Good afternoon, everyone. Can you hear me? See my shared screen? Good. Thank you. Any questions? There we go. I lost my shared screen there for a second, but I found it. Um, Announcement. Tomorrow I have to unfortunately cancel the office hour for an Oak Ridge meeting that can't be rescheduled. So if you need me for homework questions, I think I've already extended the homework deadline for those of you who've asked. So we've got plenty of time. I don't think I'm not gonna assign any more homework for this course, even though I could use your help going through the current stuff. Um, I don't want to abuse you anymore. You've been great. Um, but anyway, office hour tomorrow is canceled, and I'll send an email, I hope. Other questions, comments, or from you guys? All right. If not, you can turn your cameras off and I'll get started. Welcome back to Multigrid Methods. Today we're going to finish up slide deck number 1 for chapter 11. And if you're following along in the notes, that's chapter 11. If you're following along only in the slides and slide decks, then this is actually chapter 10. There's actually a new chapter 2, which bumped all the numbers in the book, but to keep things otherwise stable for the online community who's taking this course, I've chosen not to renumber the slides. So slide deck part 1 of 2 for chapter 10 will be finished today, and we'll start with slide deck number 2. So we're talking here about convex sets and convex functions. Last time we were proving a theorem about strong or strongly convex functions. And here's the result that we were in the middle of proving. So we were able to show 7, and we were able to show strict convexity. And the only thing we haven't done is coercivity. Since I've fixed the slides, and by the way, the new slides are available in Canvas, and then they'll also be available shortly on our GitHub repo. So we've already proved 7. I'll step back through that proof once again, just to make sure everyone's comfortable with it. And this is the notion of what we called strong convexity. The difference of these two derivative operators at two different points, W and V. Remember, those are linear functionals. And I'm going to pair those in the duality pairing with the difference of those 2 points of evaluation, W minus V. And that real number, that's what that is a real number, should be always greater than or equal to mu, for some mu, times the norm of the difference squared in the Hilbert space. So this is what we mean by a strongly convex function. This is a definition. So I want to show that if we have such a definition, or have such a function that's strongly convex by assumption, then we have this object here. And we furthermore know that E is strictly convex, and strictly convex, that has to do with the shape of the function. Remember that if we draw a secant line, it always lies above the curve. So that's what we mean by strictly convex. And we have to, what we mean in that case is that secant line is always strictly above the convex, the graph of the strictly convex function. And finally, coercive. And coercive, what does that mean? That means that as v is getting large, the norm of v is getting large, then e of v is going off to infinity. So the shape of these functions have to be like that. They have, out at infinity, we're growing off to infinity. Now, the growth could be rather slow. It doesn't have to be polynomial growth at all. It could be lesser types of growth. That's fine. It doesn't really matter. We just want growth at infinity. So this is what we're trying to prove. Starting with strong convexity, we have this. We already proved 7, but we'll go through it now once again with the corrections that I made to the draft. So what we're going to do is we're going to apply a version of Taylor's theorem with integral remainder, where the remainder involves the first Frechet derivative. And we also had a version of this involving the second Frechet derivative, but it's all we need to do is use the first. And so what we do in this computation is we're going to add and subtract that term. But as we subtract that term, we can put it into the integrand of this integral. Notice that this integral is an integral over the real variable t, and this has no dependence on t. Well, as we move this into the integral, we can attach a t to this difference here, and then we can divide by t. We can do the same thing with this difference, multiply and divide by a t, and then we can add those two things together, and when we do that, we get precisely this integral here, that in the integrand. So we've added this, and we've subtracted the same piece, but we've put it in that subtraction process into the integrand, as we indicated last time. And the error that I had in the notes was that this should have been 1 over t. So that's been fixed now. Now we look at the definition of strong convexity, and we notice that we can replace this object here by something smaller. In particular, we can use a form like this. The only difference is there's a t now attached in here in this difference. And so this t comes into that norm. And you guys pointed out, well, once I take this t out of that norm, because it's a norm squared, it becomes a t squared. So I have the situation where I have t squared over t, so that gives me 1 factor of t. But once I pull that out of the norm, that remaining quantity is independent of t and can be brought outside the norm, or outside the integral, sorry. And then I can integrate in t, and I'm just going to get a half. And so that's where we get, with equality, this term. So that's exactly 7 that I wanted to prove. That's why instead of having a mu here, we have a mu over 2. And now we just noticed that if 7 holds and v and w are not equal to each other, then this thing is always strictly positive. So if I can keep going with this inequality, I can replace this term by it's greater than 0. And if I do that, then 7 directly implies that I have this sort of thing. And by a previous proposition, this right away shows that I have a strictly convex function. So in other words, the function has that shape, right? It's a shape such that anytime I draw a secant line, the secant line is always above the graph. And of course, this is only in the one-dimensional case, and so the generalization is also true. So the last point that we have to establish, and we didn't have enough time to finish last time, is this coercivity piece. So I want to address that now. So what does it mean to be coercive? It means that as the variable gets large, then the function values of e should get large. So let's set v equals to 0 in our equality 7, or inequality 7. So we're going to set that term equal to 0. Actually, it's not, it doesn't go to 0. We're only setting v equal to 0. So this becomes e of 0, which isn't necessarily 0. Same here. This is not necessarily 0. It's just whatever that derivative value is. But we do get a simplification in that, and that term becomes 0, and that term becomes 0. And so we just have w's here and here. So that makes life a little bit simple. So 7 says that. Next, we're going to apply the property, the continuity property of the norm, but we're going to apply it with a negative sign and then throw the negative sign back. Okay, so the way we apply it is minus DE0 acting on W. This is a duality pairing, but it actually just means the action of the functional on W. So it's a function evaluation. And we know that because of continuity has to solve or has to satisfy the following inequality. So this one is the prime norm. That's the operator norm. In this case, it's the norm that you would put on the operators in the dual space times the norm of W in the Hilbert space norm. So this norm is the operator norm V prime. That's the norm on the dual space, and this one is the usual norm on the space. And now multiply both sides by minus sign. You change the direction of inequalities, and so then you'll get this term. So that's where that comes from. Now, before you do that, I guess, now you can apply Young's inequality, which says that this is less than or equal to, let's see, what do I want to use? So this guy has no coefficient in front of it. So I'm going to use a special form of Young's inequality that we've seen before, and it's sometimes called the rob Peter to pay Paul Young inequality. And let me see if I can remind you of how that goes. So I have two things multiplied together, A, B, and of course the so-called Cauchy inequality is the simplest form of Young's inequality. It says you have 1/2 a squared plus 1/2 b squared, right? But now I can change this a little bit by saying, well, suppose I start off with, let's see, I'm going to start off with AB, but I'm going to write it in a slightly different way. I'm going to say that's going to be A times alpha plus B over alpha. And now I'll apply the same Young inequality. So I get 1/2 A, and let's see, maybe we want to apply this without the square, right? So let's apply it with square root. Square root, square root. And of course you can see that this is still just A times B here, right? And still A times B. So now when I square this, I get A squared, and this guy is going to be alpha plus 1/2, and it's going to be B squared over alpha. All right, now I want to put, for one of these terms, okay, there's no mu here. There's no mu at all here. So I want to make, let's choose to operate on this guy. And let's say I want to make alpha equal to mu over 2. If I do that, then the product of this and that is going to be mu over 4. So I'm going to say, let's let alpha equal to mu over 2. And then I get mu over 4 times a squared. But what do I get with the next term? It's a little more complicated. It's going to be 1/2 b squared. And we said alpha is equal to mu over 2. So that's going to be 1 over mu over 2. So I can make this 2 over mu, right? And so I get a cancellation, 2 to here. And so I'm going to get a mu over 4 for this coefficient and just a 1 over mu for that coefficient in the end. That's precisely where these two new coefficients are coming from. Okay. And then, of course, the next thing you would do is multiply by a minus sign. Okay. Or you can start out with a minus sign here, and then when you multiply by the minus sign, you flip the sign. And in any case, this is what you get after the application of the continuity and then the Young's inequality. But now notice I have something nice happening because I can cancel that with a 1/4 coming from that. And so that leaves a 1/4 left over, or mu over 4. Okay, so that's good. All I need is for that term on W, norm of W squared, to be positive. And I've succeeded at that. So I've made that mu over 4. This term, I don't care. I don't care if it's positive, negative, or anything in between. I'm not worried about it, because I just want to be assured that this is going off to infinity. If this is negative, so what? This still goes off to positive infinity, and there's no way this can defeat that process. The C1 being negative could never destroy the fact that this is going off to infinity. So I clearly have that we're going off to infinity for this quantity, and therefore EW has to go off to infinity. But this implies that we have a coercive function, coercive functional. Okay? So that's the argument that we didn't quite have time to go into last time, but it's not too bad. Next, we want to introduce this concept of Lipschitz smoothness of a function or functional. Let V be a Hilbert space, and suppose that E is Frechet differentiable from V to R. We say that E is locally Lipschitz smooth on V if and only if for every bounded set B subset of V, and I'm going to change this to V subset equals, because I like to do that, there is a constant. Actually, no, that's not possible. We got to keep it like this, right? Because Hilbert spaces in general are not bounded. And so we really don't want it to be we want it to be a proper subset though, so that it's bounded. Okay, so it really should be proper. All right, so we say that it's locally Lipschitz smooth if and only if for every bounded set B there is a constant which is positive and depends on B. It's a little bit like, well, this constant changes for every bounded set that we're talking about. But that's okay. That's where the locally is coming from. All right. If this is so, if it's locally Lipschitz smooth, then there exists for every B such an L such that this holds. So what does this mean, actually? Maybe I could, maybe we could do a quick little example. Is that possible? Let's see. Okay, so here's the example I want to do. Let's see, how much room do we have? Actually, I'll give you an example of this in a moment. Let's get through the next result, and then I'll show you that this is not all that strange at all. Okay. So these are the so-called two-sided bounds, the thing that we sometimes called the quadratic trap, or it's related to the quadratic trap, which we will address in the next chapter, or the next section, I should say. Suppose that we have a Hilbert space and E is a functional. If E is strongly convex and locally Lipschitz smooth, then we have the following two bounds. We have this lower bound, which is true for every V and W in V. And if we take any alpha in R, then for every alpha in R, and every v and w in the sublevel set of E with respect to alpha, then we have also this upper bound. Okay, so this lower bound here is just repeated, no problem there. Okay, so if it's true for every v and w in V, then it's certainly going to be true for every v and w in a sublevel set. So the way you view this is the sublevel set. If we have a function and then we're looking down on its domain, the sublevel curves or sublevel sets look like this. They get larger and larger. Okay. And what this means is I think you all know what level curves are of a function. So the boundary here are what we call level curves, right? So that's the set of all points where Ex is equal to alpha. And the sublevel set is the set of points where Ex is less than or equal to alpha. That's why it's called sublevel. All right, so those are always going to be, generally speaking, bounded sets. Usually, I mean, not always, but usually in the way we're going to view things. So we want to show that this is the case here. All right, so the lower bound is the thing we just proved actually. Okay, that's or sorry, that we didn't prove this. The lower bound is gotten from the strong convexity. That's just the definition of strong convexity. But how do I get this upper bound? That's the question. So I want to try to establish that for some L, which depends on E and alpha. And this is the local Lipschitz constant of dE on the level set. So let's see how this works. So the lower bound is just the definition of strong convexity. There's nothing to do there. To get the upper bound, we're going to observe that the local Lipschitz smoothness of E implies that for every W and V in this level curve, this level set, sublevel set, then by definition of local Lipschitz smoothness, we'll get there in a second. Where does this come from? This comes just from continuity. Okay, so that's the continuity argument. But then the local Lipschitz smoothness says that this guy here is always going to be bounded by this object here for some L for that set. Right. So now, well, do we have it? Do we have what we need here? So this, okay. Now all we have to do is replace this z, which could be anything, with the difference w minus v, and then of course we get this upper bound. So we're done there as well. All right, so later on we're going to relate this to something called what's called the quadratic energy trap. And it's saying something important about these derivatives being trapped between quadratic differences, I guess you could say. Now, I want to give you an example and to kind of show you what's going on. This is always tricky, but because I could screw up badly and then why did it go all the way back there? There we go. Well, you just have to keep me honest. All right, so I want to consider a function which is not necessarily quadratic. Okay, let's say the function, and just to keep things standard, let's use the function e of x is equal to x, and we just want to use regular, ordinary variables, so variables in one dimension. So something like this. In fact, maybe we could say, to make our computation simple, do that. All right, now I want to show that this function is not what we call globally Lipschitz smooth. It's only locally Lipschitz smooth. And to do that, we need to calculate the derivatives of this function. The derivatives of this function are easy to get. They're just going to be x cubed, right? So for every x, the derivative is x cubed. Now, you might say, that doesn't make sense. You said that derivatives are bounded linear operators. Well, it is in the sense that this is a bounded linear operator, bounded linear functional on the real line, because all I do is if I multiply this times a real number, that's the action of the function. So it sounds a little bit silly, but that's what it is. Now, remember, to show the local Lipschitz smoothness, I have to show this. And so, well, how do we do that? So we have to subtract the derivative of E at two different points. So let's say V and W, and we'll see what we get. So if I do that, and then of course, I have to bound that by the difference of functions. And so that guy is just going to be the absolute value. So let's see how this might work. So I have to take the, oops, I need to go back and look just a second. It's going to be, okay, so that's going to be the operator norm. And the operator norm in this case is just going to be the absolute value again. So I have to take E prime of W minus E prime of V. All right, and well, it's easy enough to calculate that. That is just going to be absolute value of x cubed, or sorry, W cubed minus V cubed. Now, I always forget how to factor this guy, but I want to factor it in such a way as I bring out W minus V and then what's left over. I always forget. I think it's W squared plus WV plus V squared. Let's check to see that I've got that right. I don't want to do the polynomial division. That's awful. Okay, so it's if I take the product, it's going to be W cubed minus VW squared. Now let me do that a different way. I'll multiply through W first. So plus W squared V plus W V squared. Then minus VW squared plus WV squared minus V cubed. I think this one should be minus, right? All right, let's see, do we get the cancellation that we want? W squared V and W B squared. Yeah, so both of those cancel. All right, so I got it right, I think. Now, well, if this was to be locally Lipschitz smooth, what would I need to know? I would need to know that this is actually this part here is bounded or boundable, right? But it's not. It's not bounded if W and V are not bounded. But if W and V are required to remain in a bounded set, then I'm okay. So if W and V have to be in a bounded set, let's say an interval, then there is some L that I can find, which is going to dominate that sum. And then of course I want to leave this, I want to bring this along, W minus V. So what we say here in this case is that this functional is not globally Lipschitz smooth, but it is locally Lipschitz smooth. So there's some L for every B equal to a bounded, so we have to look for bounded sets on the real line. And let's just use a bounded interval, okay? For every bounded set. So that means that A and B are just good old-fashioned real numbers, okay? So for every B, I can always find an L such that these guys, if they're required to stay in B, okay, so that's that's like number one. So we say W and V have to remain in our set B. Then of course this calculation follows, right? Um, but now, well, and so I'm going to come back to something called the quadratic energy trap in a little bit, and it's going to be related to this topic. But basically, the main idea here is we're going to be interested in functionals that have the following structure. The functionals E, which they're going to be coercive, they're going to be convex, and I can always fit underneath such a function, no matter what it looks like, I'm always able to put underneath that a quadratic function. Okay? And that's because of the coercivity property. If it's convex and coercive, I can always find a quadratic function to go underneath this function E. So this is what we call the lower quadratic. Now, actually, the function doesn't have to be convex for this to work. It only has to be coercive. It turns out if the function is locally Lipschitz smooth, then we can always find a quadratic to fit above this function too, but only possibly on a bounded interval. So this thing is called the upper quadratic. And the combination of these two things over some bounded interval is what we call the quadratic energy trap. The energy gets trapped between two quadratic functions on some bounded set. So the set B is this bounded set in here. But this calculation, the previous calculation that I just did is related to that quadratic energy trap that we're going to be talking about in just a moment. But before I do that, I'm going to pause there and you guys can turn your cameras back on and I can take some questions. You guys, some of you have any of you taken optimization yet? 577. Okay. Lots of good clients. Um, so when you talk about convex optimization, which has some importance for things like data science and PDEs and various other things. When you talk about convex optimization, you see concepts like this, but if you haven't taken optimization, you may have never seen this before. So this is going to be new and maybe even a little bit puzzling. So just bear with me as we go through it. The reason for doing all this construction is not in vain. It's going to be so that we can say something about the the minimizers or the the extremal points of convex functions. Okay, so that's kind of what's coming up. Any questions? All right, you can turn your cameras back off and I'll get into the second slide deck then. All right, so we just finished slide deck 1 of chapter 10 on convex optimization, thankfully. And now we're on to the second one, part 2. We're talking about convex optimization. And now we set the stage, and I think we can start therefore talking about minimization of convex functionals. Okay, that's uh, it's kind of the easiest thing where we can say we have minimizers that are at least in many cases unique. So all of what we're going to be doing is looking at a function like this. It's going to be a mapping from a Hilbert space into the real line. If this was a generic Banach space or Hilbert space, then we couldn't necessarily talk about the minimization of that functional. And the reason is because, well, the Banach space over here might not be an ordered space, right? Really, the only one that you work with, which has a good standard solid ordering, which is also a Hilbert space, is the real line. So this is the most sensible place to and most sensible setting for our discussion. We want to optimize something or minimize something. So for those of you taking optimal control theory or calculus of variations, this is all completely related to that discussion there. By the way, some of this discussion that we're talking about here is highly related to to the topics that you cover in calculus of variation. How many of you, well, maybe I'll ask it another time. I think a lot of you are taking calculus of variations right now, and a fair number of you may also be taking optimal control. So a lot of these concepts are going to reappear in that setting. So we're looking for functions or points from the Hilbert space, which are arguments of this function here that are minimizers. Okay. And now a function doesn't necessarily have to have a unique set of minimizers. So what we talk about is the set of minimizers. And if we talk about a set of minimizers, we're looking for points which are in the set of the minimizers. Okay. Now we're going to abuse notation a little bit sometimes. If we know that the minimizers is that the minimizer is unique, that is to say that the set of minimizers has only one element in it, then we're often going to say we're looking for the function that is equal to the arg min EV for V, don't need to put a dressing on that, in the Hilbert space. So the way this reads is the argument that reaches or obtains the minimum for this. Okay, so the argument that achieves the minimum for this. And if it's unique, we're going to drop this inclusion here and simply say equals. Okay, but literally, the way you should interpret this guy is this is actually a set. This is actually a set. It means the minimizing set or the arguments that minimize the function. Sometimes it's also called the solution set. So just like there can be an equation with multiple solutions, there can be a function that has multiple minimizers. Now, the nice thing about what we're discussing is that there's a class of functions where we're always guaranteed to have unique minimizers. And in particular, those are convex functions that are also have some nice smoothness properties and also have a coercivity property. All right, so the following two results are pretty classical. And so for those of you who study calculus of variations, these come up in that study of calculus of variations, and they're sometimes called the direct method of calculus of variations, these two results put together. Okay, my cat is trying to make a entrance here. Go away. Do not. There you go. Go the other way. Good cat. All right. So the first one we're not going to prove because it's fairly technical. There's a proof of this one, or at least a partial proof of this one, in my other book with Abner, the Purple Monster Classical Numerical Analysis, in chapter, gosh, what is it, 15 or 16? But I'm not going to prove it here. I'm just going to state the result. Let V be a Hilbert space, and suppose that K is bounded and weakly closed, a bounded and weakly closed subset of V. And again, it must be a proper subset, so I'm not going to put the subset equals sign here. And suppose that E is weakly lower semi-continuous, right? So we defined that weird concept called lower semi-continuous and weakly lower semi-continuous a couple of classes ago, and I, I won't at this time go back and remind you what those are, but those are in the notes and in the slides. If all of these things hold, then this set is non-empty. Okay, the argmin set is non-empty. There's something in there where we're going to get a minimum. Now, notice that I'm not minimizing over all of V. I'm minimizing over some bounded and weakly closed set. And if I minimize over some bounded and weakly closed set, then, and all of these other things hold, then I'm guaranteed that there's going to be a minimizer in there. All right, so that's what is usually called the first theorem in the direct method of calculus of variations. And it explains why people were so interested in defining these things called weakly lower semi-continuous and lower semi-continuous and weakly closed and all that gibberish. It turned out to be quite useful. It's kind of the minimum requirements that you would have on a function so that you'd know that you always have a minimizer for that function. Now, in this case, notice we're not minimizing globally over the entire space. We're only minimizing over some bounded set. So that's a little bit like saying, yeah, you might have something like this, but actually we're really only interested in bounding it over or between these points here, right? So that might be the case where we have K being some finite interval of the real line and some function here that looks like this. Of course, by the eyeball norm, it's clear that the minimizer is that point there. Right? Again, we're not proving this one. This one is a little bit too far afield for us. Let V be a Hilbert space, and suppose that E is, we forgot to add convex. That's very important. E is convex, lower semi-continuous, and coercive. Then the set argmin EV, where V is taken over all of V in this case, is non-empty. So that means there's, again, a minimizer. And in this case, as I said, we're minimizing over the whole space, and so this is an important fact. Okay, when we add the coercivity and the convexity that we didn't have in the last case, and let's see, we're also strengthening the lower semi-continuity to be strong instead of weak, then we can guarantee that we have a minimizer for this problem. So how do we do this? Okay, so let's define a set B0 as the sublevel curve of E relative to this value. Actually, all that matters is that we pick some point in the range of E. It doesn't have to be E of 0. Now, you might be conditioned to think, well, E of 0 is the minimum. It's not necessarily, right? The function could be off center like that, and so its minimum could be here. And I could get even more dramatic with it. So, for example, something like that, right? So 0 is going to give me that value. That's E of 0. So that just tells me, that gives me an idea of this. It's just some number in the range, right? I know that E of 0 is in the range. So that's what I'm going to call my alpha. Alpha in this case is equal to E of 0. Okay. Well, the minimizer has to be less than or equal to that. Okay, so we're going to define the sublevel curve relative to this number. So that's definitely non-empty. It's definitely non-empty. Now, because E is convex, this set is also convex. Okay, and furthermore, it's also closed. It's also closed. So by previous propositions that we have, which I'm not going to go back and remind us of, this sublevel curve is both convex and closed. Now, by Mazur's lemma, if it's convex and closed, then it has to be weakly closed. That was Mazur's lemma that we talked about. If it wasn't last time, it was the time just before that. Now we're going to use the coercivity of E. By the coercivity of E, that's saying that the function's going off to plus and minus infinity. And so the coercivity of E is going to guarantee that this sublevel curve, sublevel set, sorry, has to be bounded. Okay, it can't. There's the argument is a little bit subtle, but it's probably fairly clear. If the functional is coercive, then actually every sublevel curve associated to a finite value from the range has to be a bounded set. All right. So now we're going to invoke the last theorem to guarantee the existence of the following of an element from this set here. Okay, so the last theorem tells us if you know something about this set, namely that what did it have to be for that last theorem? It had to be bounded and weakly closed. Okay, and we know that if it's if it's bounded and weakly closed, and if E is weakly lower semi-continuous, then we have that. But now, if it's lower semi-continuous, then it's certainly going to be weakly lower semi-continuous as well. There's a result that says that. So then we can just directly invoke the last theorem to guarantee that there's some element in that set. So that that gives us something, right? But now, is it possible that this set here is the same as this? Well, now I'm going to argue in the following way. I know that my minimizer's got to be in my in some sublevel curve. Actually, if you give me a sublevel set, and I keep saying sublevel curve when I mean to say sublevel set, well, remember how it's defined. It's going to be defined as a set of all points x such that E of x is less than or equal to E of 0, right? Well, the global minimum has to be in that set because it's got to be lower than all other points. Well, it has to therefore be lower than that point. So it has to be in B0. So that's the next argument. So if we have, if W is outside of B0, then what does that say? That says if W is outside of B0, then actually it must be a point where the energy, I'm going to call it energy because it usually is, this E function, usually called energy, is at W is bigger than E of 0, okay, which is bigger than this guy. Well, so that says that E of W is greater than the infimum for taken over B0, right, for any W outside of B0. But this implies right away that the infimum of over B0 is got to be less than or equal to the infimum over the whole space. Okay? And the reason is because this set is comprised of both B0 and its complement. All right? Well, we showed that if it's in the complement of B0, then the infimum has to be in that set. Okay? And we also know that the infimum of that set is in that set because that's how we define the infimum. All right? So we've proven what we wanted to prove, namely that this set where we have the argmin or over which we take the argmin is this exactly the same as that. And again, the reason is because V is really comprised of both B0 and its complement. Okay, so that's the argument. Let's remind ourselves what we said. Now, we did forget to put convexity in there. I'll reinsert that. But if we have E, a functional, from a Hilbert space into R that's convex, lower semi-continuous, and coercive, then we know that it's always going to have a minimizer, minimum. Okay, convex, lower semi-continuous, and coercive. All right. Now, we're going to turn our attention to uniqueness next. So let V, again, be a Hilbert space if we know that, again, E is convex, lower semi-continuous, and coercive, then this set is non-empty. Furthermore, if we know that E is strictly convex, then, and that, by the way, that's by the previous result. Previous result says that this is non-empty. But if we know additionally that E is strictly convex, then there's only one element in that set. And that allows us to write U equals the argmin, okay, in our uh, sort of our notational violation, I guess. Okay, if E is strictly convex, then this guy is a singleton set. It has a unique element in it. There's only one. And that unique element has to satisfy this. And that allows us to really say we have a minimizer. We don't just have an infimizer, we have an actual minimizer of the set. Okay? A unique object. Okay, so since E is convex and lower semi-continuous, it turns out its epigraph is going to be convex and closed. So this implies by Mazur's lemma that its epigraph is also weakly closed. Anything that's closed and convex has to be weakly closed. So we again can conclude that E is weakly lower semi-continuous by that. Since E is coercive as well, the existence of the minimizer is guaranteed. Now let's turn our attention to uniqueness. Suppose that we have two elements in V that are both minimizers, but they're not equal to the same thing. Let's show that we obtain a contradiction in this case. Two objects in the Hilbert space that are both minimizers, but they're not equal to each other. Let's show, in this case, based on all that we know, we have to have a contradiction. All right, so what we're going to do to show that we have a contradiction is let's evaluate E at the average of those 2 points. Okay, average can be computed of these 2 points because we can make any linear combination of the points from the Hilbert space, and so the average makes sense. When we evaluate that at the average, that just gives us a number. All right, but by strict convexity, this is kind of a interpolated point between U1 and U2, right? And if you remember the definition of strict convexity, we know that the secant line is strictly above the value of the point on the curve. And the secant line is represented by this, or the value of this the value at the secant line, where t is equal to a half, is exactly this. All right, but each one of these guys is equal to the minimizer, right? They're both minimizers, and so I can say that's a minimizer, so that when I add them both up, I get a minimizer. But now we found a point that is strictly beneath the minimizer. Well, that can't be according to our theory. We can, so this shows that there's another point which is strictly less than the minimizer. Okay, so that contradicts the fact that U1 and U2 are minimizers. There's another point where we get a point. There's another point, in fact, it's right in the dead center, the two interpolated values of U1 and U2, where we get a strictly lesser value. And so that contradicts the fact that these two things are minimizers. And so this proves uniqueness. And what we used there was the strict convexity. The next thing I wanted to do is argue that the minimizer has to satisfy the so-called Euler-Lagrange equation. And so again, if you guys are taking currently the calculus of variations course, you see Euler-Lagrange equation there a lot. For those of you who are taking control theory, I think Euler-Lagrange equation is also one of the topics that you discuss. But in any case, if you haven't seen it before, you'll see it now. So let V be a Hilbert space and suppose that E is strongly convex. Then the functional E has a unique minimizer. Moreover, this minimizer is uniquely characterized by the so-called Euler-Lagrange equation, which is this. So what's the Euler-Lagrange equation? It is this equation where we have the derivative of E on one side, and we're pairing that through the duality pairing with any V in the space. So this, remember, the derivative of a functional, nonlinear functional, is a bounded linear functional when I evaluate it at U. And so the only way it can make sense is if I pair it with something from the space. So this is from the dual space, and this gets paired with something from the space. And when I pair them together, it gives a number. Really, this just means I'm taking the derivative and then I'm evaluating that guy at V, and that gives a number. That's what that means. And that's called the dual pairing. That's called the Euler-Lagrange equation. So I'll give you some examples of this a bit later. Now, so let's let's have a look at the implications. So let's see, did we say that? I think here we may have to add that. I think I'm missing an assumption here. So E has to be Frechet differentiable. I think that's a missing assumption. Because if it's not, then of course we have, you know, it doesn't even make sense to write that. So let's add that as a point or a hypothesis. E has to be Frechet differentiable and strongly convex. Okay, so now if E is Frechet differentiable, as we're now assuming, that implies that it's also continuous, which along with the convexity implies that it's going to be weakly lower semi-continuous. That was the result that we had previously. Next, we're going to invoke a theorem to see that, or we do invoke a theorem to see that E is coercive. So there was another theorem that says that if we have a convex functional that is weakly lower semi-continuous and Frechet differentiable, then it's also got to be coercive. This guarantees right away the existence and uniqueness of a minimizer based on our previous theorem, or at least the previous corollary. Okay, previous corollary guarantees that we now have a unique minimizer. It exists and it has to be unique. So now we know that a minimizer exists, we know that it's unique, but we don't know that it satisfies this equation. And what we want to do is show that it does. It must satisfy that equation. So to do that, we're going to take two steps, and here they are. And so I think if we can get through this, we'll prove, well, we might get a little further today than just this, but if we can get this far, then we're going to be quite happy. So now we want to prove that the Euler-Lagrange equation characterizes a minimizer so that, if we have a solution to this, then it has to be a minimizer. And if we have a minimizer, then it must solve this equation. So should be a if and only if characterization. So first, if U in V in the Hilbert space solves the Euler-Lagrange equation, so that means at some point we're going to use the fact that that's going to be zero. Then by strong convexity said that we have this equality. That's going to be equal to 0 right away because we're assuming the Euler-Lagrange holds. And so then we just have that E is greater than E of U plus this guy because that's 0. But as long as V is not equal to U, then this is strictly positive. So we can replace this by greater than or equal to 0 with strict inequality. That says that E of V has to be strictly greater than E of U. So that says that if V is not equal to U, then it must be that E of V is always greater than E of U. This shows that U has to be the unique minimizer of E because this is a global assumption. Okay? V is anything. V is absolutely anything. And therefore, if it's always bigger than this guy, that means that this must be the unique minimizer of E. On the other hand, if U is the unique minimizer of E, then for any t not equal to 0 and any v not equal to the 0 point, then we have to have this inequality. If U is the unique minimizer. Why is that so? Well, we can move this guy to the other side, and then this just becomes any point which is not equal to, it characterizes a point U that's not, or sorry, U plus TV is a point which is not equal to U, definitely. All right, so let's see what we get. Now, E is Frechet differentiable, right? E is Frechet differentiable, so we can take two different one-sided limits. All right, so let's consider this limit here where we take 1 over t over this quotient and let t go to 0 from above. All right, so that has the limit which is just equal to this. But we said, based on this inequality here, that has to be greater than or equal to 0. Now we can take t going to 0 from below, and this changes the sign of that, right? Changes the sign once I divide by t, where t is strictly below 0, so negative. And so that makes this whole thing negative, but that also has to have the same limit. And so that says that this is simultaneously greater than or equal to 0 and less than or equal to 0. So that says the only possibility is that it's actually equal to 0. Okay. Comma, for all v in V. So this shows that the Euler-Lagrange equation holds. So we've got both directions. Okay. Right. So we said that this is a characterization. And what a characterization means is if it satisfies this equation, then it has to be the unique minimizer. And if it's the unique minimizer, then it has to satisfy the Euler-Lagrange equation. So we're done with our if and only if proof. All right, so just a couple of comments. So we've just guaranteed the existence and uniqueness of a minimizer as well as its characterization via Euler-Lagrange equation. So what? Well, that says something good because if we have, for this particular type of functional, this nonlinear functional E, then to find the minimizer, we can solve an equation, namely the Euler-Lagrange equation. This is precisely equivalent to solving for if somebody tells you that you have a minimizer locally or whatever else, that if you find the place where the derivative is equal to 0, then that characterizes the minimizer. That's exactly the same as what the Euler-Lagrange equation is saying. It's just saying it in a much more complicated fashion. So I'm going to show you how PDEs actually result from from looking at Euler-Lagrange equations for certain types of functionals over what are called Sobolev spaces. And in fact, that's how we'll derive the PDEs that we're really interested in. All right, so this says that to find the minimizer, all we have to do is solve an equation. But of course, solving an Euler-Lagrange equation may or may not be so easy. So now, the first result provides a relationship between the energy and the norm centered at the minimizer. The following estimates that we're going to show can be proven by Taylor's theorem with integral remainder, as we showed above. And so if you want more details of what I'm about to do in these calculations, you can look at the notes because, well, I would say the notes have little bit more detail, but the most important thing is if you have questions, you want to look for the references in the notes. So what are we going to be doing here? So remember I said we wanted to talk about this thing called the quadratic energy trap. Um, I need to have a really actually in the book in the Purple Monster book, Classical Numerical Analysis, I think we do have a nice picture of what the quadratic energy trap looks like. I don't think we have one put in here. No. Um, but uh, I think next time I'll bring along an example and I'll just we'll do it in detail and I'll show you what's going on there. All right, so let V be a Hilbert space and let E be a strongly convex and locally Lipschitz smooth. Strongly convex and locally Lipschitz smooth. Um, Basically, all throughout the rest of the book, we're going to be making those two assumptions about the energy functional. Okay, I'm gonna I'm going to stop pretending that this is some average run-of-the-mill function, and I'm going to call it the energy functional. That's why we chose the symbol E for this. And as I said, we're always going to be assuming, or at least 95% of the time, that the energy functional is both strongly convex and locally Lipschitz smooth. All right, so if this holds, then for all V and W and V, we have this expression. This gives a characterization of what we call the lower quadratic function. Okay, so a quadratic trap, again, I'm going to bring, I'll come back to this next time and I'll draw a nice picture for you. This is the lower portion of the trap. And then this is the upper portion of the trap. In addition, for every alpha and R, we have that if V and W are in this level set or this sublevel set of E with respect to alpha, then we also have this upper trap. Okay, so this is called the upper trap, upper quadratic trap. That's called the lower quadratic trap. Now, if we do happen to center this exactly on the minimizer, and by that we mean we're going to choose V to be equal to 0, then notice that something really neat happens. This term is 0, and that term is also 0. This term, not 0, but it's equal to the energy evaluated at 0. This term also 0, and that term also 0. And so that gives us a nice expression of the quadratic energy. Oh, sorry. Nope, I was wrong. If this guy is the minimizer, not 0, I misspoke. I don't want to make it 0. I want to make it the minimizer. If that's the minimizer, then that's 0 because of the Euler-Lagrange equation. Okay? Now I'm going to put the minimizer there. That's going to be E of U. And this is going to be U, and that's going to be U. Okay? So if this holds, then making those replacements, then we have this upper and lower bound. So U here is the minimizer. Okay? It's the unique minimizer of E. It's unique in this case because we're assuming a lot about E. We're assuming that it's strongly convex and locally Lipschitz smooth. All right, then we have this, and this really is the quadratic energy trap that we talked that I've been talking about, and that's the thing I'm going to show you next time. But I want to prove this first. I want to prove this. All right, the lower bound was already established in a previous proposition. So we already established in slide deck number one of the last results that we had was this guy. So the only thing that we have to do is establish this, and then once we have that upper bound on the where, by the way, so you need to understand that, and I forgot to point this out previously. So this mu is the mu from strong convexity, the strong convexity assumption. The L is from the local Lipschitz smoothness, and that, of course, depends on alpha in this case. So these are two different constants. Please be aware of that. So we've already established this inequality previously, and so all that we have to do is establish this guy. And the way we do that is we're going to use Taylor's theorem with integral remainder. And if we do the expansion and do the replacement, actually this falls out actually very quickly. So I'm going to leave that as an exercise to do. But in any case, once we get that, and then I go back and replace V with the minimizer, then I immediately get this. I immediately get this. For every W in the sublevel set. Okay, so as I said, the second inequality, the upper bound, follows by Taylor's theorem with integral remainder. And the fact that this sublevel set, because of the convexity of E, has to also be convex. So I'm going to let you guys, well, if I was doing any more homework assignments, you'd be doing that as an assignment. But, well, we're not going to do that. I think what I'm going to do is, let's see, do I have enough time to, I think what I'm going to do is stop the class there. We're going to pick up with this result next time. And the reason I want to do that is because even though this looks like a short proof, there are some subtleties in here that I want to go through carefully. So what I'm going to do is I'm going to stop the lecture there a little bit early, and I'll take any questions you guys have. You can turn your cameras back on. And any questions about any of this? So next time, what I'll do is I'll come equipped with a nice little picture, because this a picture makes this fairly actually trivial. It's I can create this quadratic energy trap pretty easily. And for the example that we talked about previously, that's just gonna like the 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 polynomial 1/4 w to the fourth power. This has a beautiful little drawing that anybody can do, and the result in that setting is like almost trivial. And then you realize, well, actually, this result can be generalized to the setting of having strongly convex functions and that are locally Lipschitz smooth, and it's actually much deeper than that in higher space dimensions. But basically, the picture in one dimension tells you everything that you need to know about this problem of convex optimization. Uh, Questions or comments before we all part for the day? And just remember, once again, no office hours tomorrow, but and of course, no office hours next week. So I think we will have to set up a special office hour somewhere along the way, because you've got that last homework to turn in, and I know some of you have some questions. All right. If there aren't any questions, I'll let you go. If you have any question that you don't want to share with the rest of the group, I'll stay on the line for a little bit longer. Otherwise, I'll see you guys on Tuesday. Have a nice day.
Thank you, Dr. West.
Thank you.